So, if I'll derive the Maxwell's first equation, what we can see that according to Gauss law in electrostatic, that through a closed surface, the flux means electric flux. The net, not magnetic flux, okay, the net flux passing through a closed surface is equal to the 1 by epsilon naught times the total charge Q enclosed or Q contained in the volume enclosed by that surface. Okay, so we can write that phi E is equal to closed surface integral E dot ds is equal to Q by epsilon naught. Epsilon naught is a permittivity of free space. One is permeability, now is a permittivity. And Q is the total charge, and this is the closed surface integral. So write it here, surface E bar dot ds bar. E bar is a vector, surface integral is a vector, right? So where E bar closed surface integral E bar ds bar represents the total flux passing through this closed surface is. But we know that total charge, if we'll take a volume charge enclosed by this surface, or we can say that the total charge enclosed in this surface in terms of volume charge density, rho, we can write Q is equal to volume open volume is rho dV. Now, so we can write it here that phi E is equal to closed surface integral E dot ds bar is equal to Q by epsilon naught, where Q is equal to, in terms of volume integral, rho dV. So we can write volume integral rho dV. Now epsilon naught into dot E is equal to, we can write D is equal to epsilon naught E. So we can write D bar, where D is the electric charge density, right? D bar is dot ds bar V rho dV. Rho is a volume charge density and D bar is the our flux that means electric flux density, right? This is the volume charge density and this is the electric flux density. Now Gauss divergence theorem, if we apply here, then we know that closed line integral, closed surface integral, we can convert in a volume integral. So we can write volume integral divergence d bar dot dv bar, that is equal to, sorry, closed surface integral to, we can convert it in open volume integral. So open volume integral divergence d bar dot dv bar, that is, here you will write here closed, okay, give a sign of close. So volume integral rho dv. Now we can write divergence d is equal to rho. So divergence d is equal to rho. Now if the volume charge density rho is equal to 0, that means in free space, then we can write divergence d is equal to 0. This is the Maxwell's first equation in electrostatic field. We have seen the magnetostatic field, the divergence B is equal to 0, magnetic monopole doesn't exist. And Ampere's law in static field, we have seen that curl H is equal to, we have got Ampere's law from that curl H is equal to J, right? And the third equation, if we'll go, that is a magnetostatic field and electric field. You can see here that electric field and magnetic field both are present. Now what is this? So a static electric field intensity, we have seen that E bar can exist without we can say that magnetic field H. Whenever you have taken capacitor, you have seen that static electric field intensity E bar is present and there is no magnetic field. Now, similarly, if I'll take a conductor and current is flowing, steady current is flowing through this conductor, magnetic field intensity H bar is present without any electric field, right? So, electric charge induces electric field and electric current induces magnetic field. So, as long as a charge and current distribution remain constant in time, there will not be any change in the field that they induce. So we can say when the charge and current sources are varying, that means if I'll take the time varying charge or time varying current with respect to time, if I'll take it, the field will also vary, right? So what I want to say that without, that means in the first case there is no variation of field. If I'll take the charge, that will induce E, electric field intensity, and if we'll take current, it will produce magnetic field intensity, right? But there is no variation of electric current or electric charge. Now we are taking the variation of electric charge and electric current. So what will happen? That means we are taking a time varying field, because if we'll change suppose if I vary the current, that means that will vary the electric field intensity, that means that will vary the electricity, that means that will vary the electric flux, magnetic flux density, that will vary the magnetic field intensity, and that will vary the magnetic flux density, and that will vary the magnetic flux, because steady current is now time varying current. So these time varying fields are known as dynamic field. Previous was static field, now it's a dynamic field. And here we can see that E and we'll see, that means when next third equation we'll see that E and B are interconnected and they are coupling. So this equation, third equation, is connected to a electromagnetic field, or we can say that produces an electromagnetic wave. And here from this we can say Maxwell's four equations are connected to a electromagnetic wave. How? And from these last two equations we will see that time varying field, if we'll consider, we'll get two equations, and this will directly related to a wave equation. So electrostatic and magnetostatic are special case of electromagnetic wave fields. Electrostatic corresponds to a stationary electric charges, and magnetostatic corresponds to a steady current. And these two are related to a electric field intensity and electric flux density. And another case is current and magnetic flux density and magnetic field intensity. So we can write D is equal to epsilon E in electrostatic field, and in magnetostatic field we can say that B is equal to mu H. and we are taking in a linear zone. Remember. Okay. Now, if I'll take a time varying field, that means when a wire, a conductor moves through a magnetic field by cutting its flux, a voltage is induced because now conductor is moving but field is stationary. Now, if I'll take a stationary conductor and varying magnetic field, that will cut the stationary conductor and it will induce EMF. So, there are two conditions we are getting. One, either the conductor is stationary and magnetic flux is varying, time varying, or magnetic flux is stationary, the conductor is moving. Both cases we are seeing that flux is cutting. So in there is a rate of change of flux. That means there is a each and every moment flux is changing. So there is an induced EMF. So we can write V EMF is equal to minus d phi by dt. And this electromotive force unit is volt and phi unit is Weber and T is in second. Now according to Faraday's law, what Faraday's law states? Faraday's law states that the magnitude of electromotive force induced in a conducting loop is equal to the rate of change of magnetic flux through that loop changes with time. Or we can say that VMF or induced EMF E, if I'll take, or you can take here epsilon, because E we have already taken electric field intensity. So you can take here epsilon, that is equal to minus d phi by dt. This small e you have, or you can take a small e, because there we have taken capital E, so we can take a small e, that is equal to d phi by dt. Now according to Lenz's law, we can say this is a minus, right? If there is a number of turns, n number of turns of coil is present, then we can say that V is equal to minus n d phi by dt. Now the second part. If I'll take a coil, circular path, suppose we are taking a circular path, and a particle of charge Q0 is moving around the circular path. Suppose Suppose I am taking a small circle and uncharged particle is moving around this circular path. Okay, and the radius. When it is moving through a circular path, this charge is q naught. The work done on it one revolution by the induced electric field is W. Suppose I am taking W. So W is equal to, you can write closed line integral F F dot dl. Now what is F? F is equal to, electric field, that is equal to q naught E bar. So L, what is L? L is the total. If I'll take it F closed line integral dl, then we can write F into L. Now L is now 2 pi r. Right? So if I'll put it here, q naught E 2 pi r. So what we can write? what we have seen, W is equal to Q naught epsilon, where epsilon is equal to nothing but E power 2 pi r. What is Q naught E? This is epsilon, okay, and that is equal to E bar 2 pi r. Now what is Q naught E? That is force, the magnitude of force acting on the test charge. And 2 pi r is the distance over which that force acts. Okay. Now, if I'll write here that epsilon is equal to closed line integral E dot dl. So you can see this is a closed line circle, a circumference of circle, right? So we can take a closed line integral for this purpose. So we can write epsilon is equal to closed line integral E dot dl. Now what we have seen previously, we have seen that epsilon, that means induced EMF. This epsilon is induced EMF, that is only possible minus del B by del T. If there is a rate of change of flux, then we can say that induced EMF will happen, and rate of change of flux means rate of change of flux density. So we can write that epsilon is equal to minus del B by del T from Faraday's law. And here we are saying that from work done in a closed path of a test charge, from this we can see that epsilon is equal to closed line integral E dot dl. That means electric field intensity. So if I'll equate both, then we can write that this is equal to minus del by del T So what this equation says that a changing magnetic flux or flux density induces an electric field. Previous case, what we have seen, that if a static current is flowing through a current, if I'll take a conductor and if a static current is flowing through this conductor, magnetic flux is induces, as a magnetic flux induces, right? So now what we are taking, that the current, somewhere that current is time varying, so magnetic flux is now changing. So from this we are seeing that if magnetic flux is changing, then there is a there is a concept that electric field intensity is coming, and this electric field intensity is, we are taking a closed line integral E dot dl is equal to minus del B by del T. So now In time varying field, we are saying that in static field, static electric field, there is no magnetic field, there is no electric field. But now, if the magnetic field is varying, we are saying that electric field is coming. So, we can write so what we are saying, closed line integral E dot dl is equal to minus del v by del t. So if I'll take this del by del t is outside, minus del by del t outside, and we are taking b bar dot ds bar, and here we are taking that this closed line integral E dot dl, we can apply Stokes theorem, then we can find out, we can convert it line integral to surface integral. So open surface integral curl E dot ds, and that is equal to minus del b by del t dot ds bar. So we can write curl E is equal to minus del b by del t. So what we are saying, that flux density is now varying, which is produces a rotating electric field. So this is the Maxwell's third equation. And this form, if I'll take it, this is the differential form and this is the integral form, right? So if I'll take a question that a circular loop conductor of radius 0.1 meter lies in the z is equal to 0 plane, that means xy plane, and a resistance of 5 ohm give given, actually V is equal to 0.2 sine 10 to the power 3 T AZ cap Tesla. Find the induced EMF and the current. So this problem will solve, and some problems will also solve for different Ampere's law and these cases. Now due to some issues, network issues, due to some laptop issues, and the problem due to the monsoon weather, that's why this video is not, the quality of video is not so perfect. So just adjust for this week. Next week, hope that will take that means the this class will be conducted properly.